Okay, so thank you very much to the organizers for inviting me. In the last 2 days, looking at the program and attending some of the presentations, I feel that I'm a bit of an outsider, and I think I'm right. So that's why I changed the content of the presentation a little bit with the view to step back and give you a bit of a background story till we come to quotient learning. In particular, I will tell you the kind of variational regularization problems that I will focus on, and give you one particular point of view, which is inverse scale spaces. That is interesting both to understand what regularizers are doing, but also, and quotient learning will be one of the things, the cool things that you can do with the inverse scale space point of view. Okay, so this presentation includes joint work with a couple of people. Let me point out in particular Martin Benning, who is really the Cambridge person behind inverse scale spaces. And you will see later on, you will notice it, I'm sure, that I've clumsily used some of his slides. He knows about that. So I'm not stealing them. Okay, so that's the outline. First, I'll give an intro to variational regularization and where scale spaces appear. And then I'll talk, as I said, about the inverse scale space flow and give you 3 use cases of where the inverse scale space point of view gives you a natural way forward to deal with some applications, or, as I said, to understand what regularizers are doing. Okay, so first of all, very briefly, the kind of notation that I'm going to use. So I will mainly be speaking about image processing. So the data that I'm acquiring is an image or some transform of an image that I want to retrieve. This image lives on a rectangular domain, and I call it F. So F is the imaging data that I'm measuring that could well live on a slightly different domain that I call omega tilde. And what I want to compute from F is an image U. And then U and F, as I said, they could be related via some forward operator, and I will make some assumptions about this forward operator as we go along. In this presentation, I will probably quietly sometimes switch between U and F living in infinite dimensional function spaces, and so the continuous point of view, and U and F being vectors in Rn. And I think you will see when this is happening. Okay, so first of all, this presentation is actually based on a presentation that I gave last year in a conference on operator theory, where my first question was already, why are you inviting me to this conference? And what they wanted me to do is to talk about differential operators in image processing. And you will see how this is related to inverse scale spaces in a moment. So let me first tell you where differential operators or differential equations appear in a natural way in image processing. And that is image denoising. So the image F that is given to me is a noisy version of an image U that I don't know, and I want to compute an approximation of this image. So this is the classical denoising task. And so one way to denoise an image is Gaussian filtering. We all know about that. I just picked Gaussian filtering as a starting example because this is the first instance where a very simple differential equation appears, which is the heat equation. And the connection is that if you start the heat equation with your noisy image and you let it evolve, a solution to the heat equation over time is nothing else than a Gaussian filtered version of F, where the width of the Gaussian kernel is related to the time until which you have evolved the solution. And you see one example here. So people very, very soon moved away from just Gaussian filtering because of the obvious disadvantages that you can see here in this evolution, which is it's an isotropic filtering, it's homogeneous all over the image, it doesn't depend on structures in the image itself. So this is when PDE people got also a bit more interested in that. One of them is Perona and Malik, which turned the linear diffusion that you can see here in the heat equation into a nonlinear diffusion, weighting the diffusion with a diffusion coefficient which should aim to diffuse less in areas where something is happening, which is quantified by the size of the gradient of the image, and should diffuse more in areas where the gradient of u is small. So this is given here. How does this relate to variational regularization? So if you go back to the heat equation and you just discretize the heat equation in time and you do one time step, then you can phrase the solution after this one time step as a minimizer of a variational regularization problem, which is here, where the weight, how much you're regularizing, is correlated with the time step that you have taken. And the same you can do with the nonlinear diffusion. And formally, you can relate that to a minimization problem with what is called the total variation, which probably most of you have heard about, which in another point of view you can think, as I said, in terms of a nonlinear diffusion type regularization, but you can also think of it as a sparsity promoting regularization that promotes sparsity on the gradient of u. Okay? And again, you can see the evolution of this here. So this is the kind of setting. And now I've talked about denoising. Well, this is just to make it, let me get to this later. So you can do this for any kind of convex functional. You can phrase it both in the PDE or the variational regularization setting. And just to finish off with that is that this type of regularization really complements the messy data we are starting with, the noisy image, complements this with the prior assumption that the image I want to reconstruct is characterized by just a few relevant geometric features, which in the total variation case are the edges. Okay, so eventually I want to go beyond denoising, and I want to solve inverse problems like this, ku equals f, where k is a bounded linear operator from a Banach space where u lives to a Hilbert space. And just to give you two examples of where this appears in image processing, the kind of things I have in mind is when k is a blurring kernel, for instance, when what you're measuring is a blurred version of what you are interested in retrieving. Another prominent example in image processing is tomography. So in this case, the data you're measuring are projections of the image that you want to retrieve, usually noisy projections. So noise is always there in the kind of things that I'm looking at. And so in this scenario, we can again have these two different points of view, the variational framework and the PDE, formulation of this, where this really, I'm stating here that this is the corresponding gradient flow to this variational regularization approach. But this really also holds for J being non-differentiable. So in this case, you have a family of gradient flows defined by the subgradients of this functional J of u. Okay, so this is somehow the setting I'm in, and this last statement on the slide is kind of important also to motivate the inverse scale space point of view. So you can think of that, by the way, as the scale space point of view, right? You're going through different scales of the solution as you evolve along this PDE. What you also realize when you look at this variational regularization approach is that this functional J, the regularizer, naturally introduces a bias in the solution, which is usually in the kind of regularizers that I'm looking at, given by a loss of contrast. And it's important to remember this when I go to the inverse scale space setting. So the kind of regularizers, let's set the stage. The kind of regularizers I'm looking at are functionals J that are convex. Okay, so I'm still looking at convex problems. My operator K is linear, so everything is nicely convex. And that are one homogeneous. So the L1 norm is an example of an absolutely one homogeneous functional. That is a semi-norm, so fulfills some of these properties here, so non-negativity, triangular inequality, and it has a subdifferential characterization, so you can characterize gradients of this functional J by lying in the subdifferential. Okay, so you should stop me. I'm rather quick because this is kind of standard for me, but if it's not standard for you, stop me, okay? So some examples, as I said, L1 is one example of regularizer that falls into this family. The total variation is another one, and I'm just showing you this because I might show you an example later on of this total generalized variation. It's just one example of a bit more complicated regularizer in this framework, which is a type of informal convolution between total variation and second order total variation regularization. Okay, so these are the kind of regularizers I'm interested in. And I said these regularizers really encapsulate some geometric prior information I have about the images U I want to reconstruct, and I've tried to say this in words below each of these regularizers. So in this case, the minimizer is assumed to be sparse. In this case, we are assuming that the minimizer is piecewise constant, so the gradient is sparse, and in the total generalized variation case, U hat is piecewise linear, or piecewise linear and piecewise constant, kind of. Okay, so now let's turn to the inverse scale space flow. So so we have seen the scale space point of view, which was this gradient flow. Now, I said that this point of view introduces a bias in the solution. For instance, a loss of contrast. So one way to get around this is not to solve the penalized regularization problem. So this Ku minus F, Hilbert's norm squared plus a penalty that is the regularization, but to solve the constrained problem where you're minimizing the regularizer such that Ku equals F. Your forward model is fulfilled perfectly. And of course, in most situations, you don't want to solve this exactly because you don't want to go to the noisy solution. But you might still want, and I'll motivate this in a second, you might still want to aim to solve this and then stop early. So this is kind of the motivation behind this inverse scale space point of view. So I'm starting with a discrete version of inverse scale space, which is the Bregman iteration, or more commonly called augmented Lagrangian approach to solve this constraint optimization problem. This amounts to a minimization problem like this for UK plus 1. The constraint Ku equals F is integrated into that in terms of a Lagrangian, an augmented Lagrangian term with Lagrange multiplier P, which in this case turns out that this Lagrange multiplier is an element in the subdifferential of this regularizer. And then the thing you need to do to solve this is you need to compute the minimizer of this problem, which is almost the same as the penalized problem, and then you update the Lagrange multiplier in every iteration. What you can show is that in the limit, you are solving the constraint optimization problem, as I said before. Now, why would you want to do this? The key idea is that in the gradient, in the forward scale space point of view, what we have seen is that we're introducing a bias in the solution. Now, the idea here is you're starting with an initial condition, let's say that is 0, that is in the kernel of the regularizer J. And then you are, as you go along, you're reintroducing scales. You're reintroducing first the larger scales, and then you're reintroducing the smaller and smaller scales. Versus in the previous consideration, we're starting with the noisy image, and then we're attenuating more and more scales. So that's why it's the inverse scale space point of view. And the idea is that although you don't want to solve eventually the KU equals F problem, you are able to, if you stop early and when to stop, you can use different stopping criterions. One of them is the discrepancy principle, which is something that if you have an estimate on the noise level, you are stopping the moment your discrepancy principle is violated. And if you do this, you can show that you are actually able, and just look at this, which is just a one-dimensional slice through, this is a magnetic resonance tomography experiment, but that's not important, through the solution of such an inverse scale space iteration. You can see that the green, which is the Bregman reconstruction, has regained some of the lost contrast that you have in the penalized reconstruction, the Tikhonov reconstruction. So one of the ideas of this Bregman iteration very initially was to get rid of the loss of contrast that that this one homogeneous regularizers J, like the total variation, show. Okay, to make a connection to something you might be a bit more familiar with, special cases of this Bregman iteration appear when you linearize it, which means that here instead of UK plus 1, you're taking UK. And in this case, you're ending up with a generalized Landweber iteration. If you choose as a regularizer the Banach space norm squared, then you're just ending up with iterative Tikhonov regularization. Now, what is the inverse scale space now? The inverse scale space is the continuous version of this. It appears when you interpret alpha, or better 1 over alpha, as a time step, and then let this time step go to 0. And if you do this, and remember this alpha was the weight in front of the regularizer. So if you do that, you end up with a differential equation for the Lagrange multiplier, for this P, the subgradient of the regularizer J. And again, you can show that if you evolve along this equation, in the limit you will recover KU equals F. Okay. So let me say that the people who have really coined or have really looked into Bregman iteration and this inverse scale space, the continuous point of view of Bregman iteration, are really the Osher group, Martin Burger, Martin Benning, Guy Gilboa, these kind of people. So some of the references, even if I don't say them, they will appear on the slides. Okay, so let's see one example of such an inverse scale space iteration. And this will also connect to some of the use cases that we will see later on of why the inverse scale space point of view might be interesting. So this is my input image, F. And what I'm doing now is I'm showing you the inverse scale space iterates UK plus 1 for the particular choice of regularizer that is the total variation. And what do you see? They show, and in which sequence do they show up?
Biggest to smallest.
Yes. Yes. So this is what I said before, right? So you are starting with reintroducing the larger scales, and then you're reintroducing the smaller and smaller scales. The other thing that you see, if you look at UK plus 1, it's exactly F. Or f probably up to a loss of contrast if I haven't yet gone with k to infinity, right? And this is another thing. What the inverse scale space allows you to do is to analyze functions, images, which are singular vectors of the total variation, and these singular vectors, I will define in a second, are functions that can be reconstructed exactly up to a loss of contrast. And this is quite interesting to think a little bit about these type of functions and what are the functions that such a regularizer can reconstruct exactly, because this gives us an understanding of what the regularizer is doing. What are the structures that this regularizer is very good for? And circles are one type of these singular vectors that lie of the total variation, and they pop up one after the other in this inverse scale space point of view. So, use cases. The first one is spectral filtering. So what do we want to do usually with images? One example is something like this. You have an image, and what we have seen somehow in this inverse scale space is that we can get a handle on the scales in the image by letting the image evolve along the inverse scale space flow. So by the way, now you can see my clumsy stealing of slides of Martin. So this is my given image, and in a lot of scenarios you might want to decompose this image into the low frequency component and the high frequency component. Think about denoising or texture decomposition, for instance. And how to do this. So if we go back to the inverse scale space point of view, and you're starting the inverse scale space with f bar, which is a projection of f onto the kernel of j. So in the case of the total variation, this will be just be the average intensity over the image. Then you can define a nonlinear spectral transform out of this inverse scale space flow by the following consideration. Define phi as ut. And then look at the integral of phi with respect to t. This is the integral of ut. And also use that we know in the limit u of xt equals f. So if I take the limit of u of xt minus u of x0, which is exactly this integral here, this is f of x minus f bar of x, my starting point, which means that f of x can be written as the integral over ut plus f bar of x. So how can we turn this into something practical? So phi was ut. Let's in the discrete setting, let's define phi k to be u1 for k equals 1, and then the difference between consecutive iterates for k larger than 1. And then write f as the sum over the phi k plus the f bar. And then you can get something like this, which Martin also calls the B composition. So you start out with an image f, and what I'm showing you here are the scales, the phi's that appear in the spectral decomposition in this spectral decomposition of f. So my spectral decomposition is defined via these phi k's. And again, what you see is that you pick up different scales in the solution. So why is this useful? How can this be useful? Well, you could use this to do, for instance, some low-pass filtering or some high-pass filtering or some band-pass filtering. And you can do this to, for instance, phrase the initial example that I've shown with the Mona Lisa, where you want to decompose the high-frequency components by just saying my f tilde is just one part of the spectrum, leaving out the part of the high-frequency components, for instance. So my f tilde, for instance, is this one here. And you can do other kind of funny things if you now combine that with some other image processing tweaks. So this is a picture of Trump. This is a picture of the Lincoln statue. Now, okay, this is, I hope you have a sense of humor. So, okay, so Trump is making everything great again, in particular the Lincoln statue. And what has happened here is that we took, and I'll explain this in 1 second, we took part of the spectrum of this nonlinear spectral transform of Trump and put that with, as I said, some image processing tweaks, detecting the face and things like this. We put some of the scales of Trump onto the Lincoln statue. And of course, Lincoln doesn't like this very much. And you can do a similar thing with Hillary, who says, well, not even the American people would seriously consider playing the Trump card. And after the election, she brought back to reality, let's say. Yeah? Okay, so and the idea is these are the image processing tweaks. I'm not going into that, but it's a sequence of face detection, detecting the eyes and stuff like this. The filters are also not just filtering in the spectral domain, but they also filter spatially, because you might want to keep certain features like the eyes or stuff like this of the original person and only want to replace stuff on the skin, for instance, only get the wrinkles from Reagan onto Obama and things like this. Okay, so this is just what I said before. So you have these filters. This is, by the way, not Reagan anymore, not morphed into Reagan, but can anyone guess? Yes, oh wow, very good. Yeah. Okay, so let's be a bit more serious. I said also that this inverse scale space flow can be used to understand regularization a bit better. And let me say a few words about this now. Okay, so the idea is I want to use this inverse scale space flow to compute singular vectors of the regularizer. And how is this connected to each other? So again, I start with my inverse problem, ku equals f. Classical singular vectors are defined like this. And the singular vectors are building blocks for the solution. And this is why it's interesting. U can be written as the sum over these singular vectors. Okay, so this is in the classical scenario, but now I'm regularizing with something very nonlinear, right? So how do I do this? So this is the key question. How do I move, how do I go from this classical point of view of singular vectors to computing singular vectors of something that is very nonlinear, a nonlinear operator, like subgradients of the total variation. So this is just to remind you, these are already singular vectors that are popping up, but can we use that to analytically understand what is going on? Okay, let me skip that. We want to do this really for problems also where we have a forward operator involved. Up to now, what I'm showing you here is without a forward operator, but we want to do this with a forward operator for various reasons, because they appear in image processing a lot. And so the question is, can we, if we assume that my image f is the sum, or not, could be an image or some measurement of this image, if I know that this is written as the sum of gamma k times k u lambda k, where u lambda k are these type of singular vectors, can I recover with the inverse scale space flow one of these singular vectors after the other? Under which circumstances can I do this? So what is this generalized singular vector that I'm talking about? And here's the definition. So what I'm now defining is a singular vector u lambda is now a function u lambda that fulfills this differential inclusion. Lambda k star k u lambda is in the subdifferential of the regularizer j of u lambda. I want to consider only the non-trivial cases, so u lambda not equal to 0, and I'm normalizing just to get rid of this additional degree of freedom. I'm normalizing with respect to k. And then I call u lambda the eigenvector, or the singular vector, of j with respect to k, and I call lambda the corresponding eigenvalue, which is just the functional j, the regularizer j evaluated in u lambda. Okay, so this, if you now take j as something that is differentiable, so just the gradient of u in L2 squared, for instance, and k equals to the identity, this actually brings you back to the usual notion of singular vectors, which are the ones for which minus lambda f equals the Laplacian of f. Okay, but you can do more, because you can now look at that for non-smooth regularizers, not differentiable ones. And what I'm showing you here are eigenvectors u lambda of the total variation for k equals the identity. And this is something that is again well known in 1D. These are just one example of step functions. Or more generally, actually, eigenvectors of the total variation in one dimension are all the Haar wavelets. Okay, let me not go there. You can also do this in 2D. So these are typical eigenfunctions. This is a typical eigenfunction you get for the two-dimensional total variation. This is a typical eigenfunction you get for the second-order total variation. And this is a typical eigenfunction for the total generalized variation, which is this informal convolution between total variation and second-order total variation. Okay, so I've not shown you that this actually works also analytically. So let me explain to you or show you that this indeed works. And I want to motivate this by looking at the approach of Showalter. So if I look, if I just take j as the gradient as the L2 norm squared of u, then the inverse K space flow just simplifies to this gradient flow here, which is Showalter's method. And if I assume that K is compact, then I can express u of t in terms of its singular vectors, the singular vectors of K. And this is just a slide to show you how this looks. So I have Vj, I have Uj, and also normal basis of the range of K and the range of K star. And my sigma j are the null sequence, such that these two relations are fulfilled, just as we started out before for the classical eigendecomposition. Then I can write u of t in this way. And in particular, if I assume, and this was, if you remember the assumption I've started out with, if I assume that f is actually a linear combination of k of these eigenfunctions, then my u of t is also a linear combination of these eigenfunctions. So I can recover the eigenfunctions as parts of the solution, and they will pop up one after the other, depending on their eigenvalue. So what about if I now have if I'm now in this more general setting of functional j that is not differentiable, of this one homogeneous functionalist j, then again, and this is something that the two Martins have shown, Martin Burger and Martin Benning, they have shown if I start out with just one eigenfunction, so f is just the operator k applied to one of these eigenfunctions times some gamma, then u of t for a critical time t1, at a critical time t1 will show this eigenfunction. So the eigenfunction will pop up. And this is where you see that for the total variation, the step function pops up at one particular time t. I've glimpsed over everything here that I'm always showing here on the right. These are the subgradients. So these are the dual variables to u. Okay. Okay, so what about if my f is now a combination of more than one eigenfunction? Then you can also show something similar, but you need an additional condition. So I will not go there because I will want to tell you a little bit about the quotient learning again. But you will need an additional assumption that we've called the sub-zero condition, which you can think of as a condition that says that the subdifferential of J is linearizable in the eigenvectors uj, or in this k star k u lambda j. Under this condition, you will have the same property, and I think I'm going to skip this. What I was going to show here is that if you start out with three very, very simple eigenfunctions like this, u lambda 1, u lambda 2, u lambda 3, then as you go along, and this is now for j of u just being the L1 norm, you start out with these three eigenfunctions, so this one, and this one. Then you, along the inverse scale space, they will appear one after the other. This one first, then this one appears, and then this one appears. Okay, up to a loss of contrast. Okay, now let's go to the quotient learning, which is the original title that I had. And this is now yet maybe a surprising situation where again the inverse scale space appears. And I'll show you how. So the idea that we started out with is that we wanted to have a learning mechanism that learns, so starting out with regularizers of this type, L1 norm of u convolved with some kernel h. We wanted to find an h such that h gives you a very, very sparse representation of some exemplar u pluses and gives you a very non-sparse representation of some exemplar u minuses. And this is also where this learning from mistakes or involving both wanted and unwanted outcomes comes into the play. So what you want to learn is a good sparse representation of u, such that you get a sparse representation of these u pluses and that are very bad for u minus. Initially we thought, although this then didn't end up anywhere, we just thought we are just going to take as u minus noise. And we take as u pluses any structure that we want our J to recover. But you'll see a bit more interesting examples in a second. Okay, so the aim is to learn this filter. And of course you have seen instances of learning such filters, for instance, in dictionary learning. But the crucial difference to these type of approaches is that now we also want to learn from negative examples. Okay. Now, how is this related to inverse scale spaces? So now when you look at this, you might wonder, I don't know, maybe you're better than me, but initially I thought, I mean, how are we ever going to solve this quotient minimization numerically? And this is the nice thing where inverse scale spaces pop up, because this quotient actually turns out to be nothing else than the Rayleigh quotient of a generalized and nonlinear eigenproblem. That is this one. So you start out with two convex functions r and s. You look at the subdifferential of r minus lambda subdifferential of s, and look for a solution of 0 being in this difference of subdifferentials. And then if then it turns out that for this to hold, this lambda here actually is nothing else than just the quotient between r and s. And just to compare this with the linear eigenproblem, in the linear eigenproblem you have a f minus lambda f, and the Rayleigh quotient being this guy here. If you turn this into a numerical iteration, you end up with the inverse power method here on the left. So what you're doing basically is that you're linearizing, and I should stop, this means, which I'm doing in a moment. You are ending up with an iteration that is aiming to solve a linearized version of the subdifferential inclusion, which you can also phrase in terms of this minimization problem here. Fk plus 1 is the argmin of, and now this might remind you of something now. It's exactly the inverse scale space that we have seen before for this regularizer R. So now instead of J, I've used R, but it's the same as, has the same meaning as my J before. Okay, so this nonlinear inverse power method is actually due to Hein and Bühler from 2010. And it really looks like this. And this is where you see that the inverse K space appears. And this is what we are using to solve this quotient minimization problem. Okay, and here you see the Rayleigh quotient. Okay, so well, this is just again for our scenario, how this looks for our two J's with U plus and U minus. It looks like this. So this is the same as before, just putting in a J of U plus of H and J of U minus of H for R and S. And now what can we do with this? So one thing that we looked at is to use this quotient learning for training a regularizer that is given by an infimal convolution of different terms. So now you can think about it like this. You want to solve, now in this case, n filters, hi, which are very sparse for the ui, or the ui's, you could have more than one, and very non-sparse for all the rest of them, for all the uj's. And what we then want to do is to use this as an infimal convolution regularizer, where U is a sum of U1 to UN, and the AJs, the HJs, are linked to the UJs for which they are sparsest for. Okay? So this is the idea. So what can you do with this? Just start with U1 and U2. This is U1 plus U2. This is the ground truth. So you want to decompose this one into U1 and U2. And you want to learn the optimal filters to do so. These are the guys that come out of the quotient minimization, which seems quite natural, in fact. And if you then use those, H1 and H2, in an infimal convolution setting, so you throw those into the infimal convolution regularizer, constrained to U1 constrained to the starting point U, then you get something like this. So you really get the decomposition into U1 and U2 up to some error. That is the natural loss of contrast. You can do this for other things. These are for diagonal patterns. Again, you actually get filters that are really doing this decomposition for you. And there are more examples, but obviously I will not show them to you because of time. But I want to finish off with one more example, which shows that this very, very trivial type of representation of an image U can be used for machine learning. And so here we're looking at the MNIST database. I guess all of you know what the MNIST database is. Digits from 0, handwritten digits from 0 to 9, 28 times 28 pixel images. And what we want to do is we want to classify them. And initially, we just looked, because the code was running then for 2 for two images, U1 and U2. We just focused on two classes, and we chose 0 and 3. And now we did two experiments, okay? One of the experiments is the top one, which is for both of these classes, we are feeding our quotient minimization with a subset of the 0 class and with a subset of the 3 class with images from these two classes. And we are learning two filters, H0 and H3, that are for which the zeros can be represented very, very sparsely, and for which the 3s can be represented very sparsely. And then we did a second experiment where we learned both filters, not only taking into account its own class, but also taking as a negative example into account the other class. Okay, so which is this quotient minimization idea. So the first one are the H0 and H3, and the one with negative examples are the tilde versions of those. Okay? Okay, and this is what comes out. These are the optimal H0 and the optimal H3 from the first experiment, and these are the optimal ones, the tilde versions of those from the second experiment with negative examples. And you can see, if you use this now in a classification way by saying it's the class for which U can be represented in a sparser way, so you take the minimum of H0 convolved with a test image in the L1 norm and H3 convolved with the U test image in the L1 norm, then you have this kind of success rate. And if you do it with a quotient, you have this success rate. And I mean, this is not at all impressive for MNIST, where this can be beaten by a lot. But it's a very simple way to do it. It's extremely simple. And the only thing that I want to show with this is that this incorporation of negative examples is actually worthwhile to do. Okay. So takeaway messages are that scale spaces or inverse scale spaces are an interesting point of view onto variational regularization for different reasons. I've shown you some examples where we can use them for image fusion, picking out different spectral components from images and putting them onto the other one. We can use them to understand the building blocks of regularizers via singular vectors, and they appear in this quotient learning approach. And there are lots of open problems and lots of potential directions one could go to. Maybe because I've finished with the quotient learning example. For those of you who know a little bit about neural networks, there is the kind of obvious question that appears is how are they related to these adversarial networks? Because it seems that conceptually we're trying to do something very similar, but probably quite differently. Okay, so thank you very much.
Thank you to all the speakers again. And I'm afraid we are running out of time. But please don't run away, even if you're a bit hungry, because we have to take the group photo. So I think we should all follow Richard. And
So for group photo now, and for those of you who are going to dinner in St. John's this evening, if you want to meet in the foyer at 7 p.m. sharp, then we'll walk over there together.
How to meet in the foyer if we don't have access to the door?
Just outside.
Okay, but so be on time.
Sharp time is important.
Yeah, exactly.